right, guys. I'm looking forward to coming around and checking that homework assignment. That one problem. Don't get my hopes up. Well. All right. So in the homework problem last night, they gave you the surface area formula you had to optimize, right? But it was in two variables. It had the r's and the h's. But we know the volume of a cylinder, right? Yeah. Pi r squared h, area of a circle times height, and that was equal to 1,000. So you solve for h with that one, and you plug that into that primary equation, the equation for the surface area. It was now in one variable. And then you just have to take the derivative. What did you get for the derivative? The 16. Oops. Yeah, 16r. Wow. Okay, off by a little bit. Yeah, r minus 2,000 over r squared. You set that equal to 0. So we'll go over that. But today's do now is really a summary of the lesson. And so today's do now, please do your best job, because if you understand the do now, you really will understand a big part of the lesson. So let me be very clear what I want you to do. I want you to sketch y equals x squared. You know what that looks like, right? Yeah, it's a parabola, right? Then I want you to go to your parabola and draw the tangent line for the parabola at x equals 3 and write an equation for the tangent line. And then I want you to figure out the y coordinate on the parabola when x equals 3.1 and on the tangent line when x equals 3.1. All right, so you're going to sketch the parabola, draw the tangent line at x equals 3, write its equation, plug in 3.1 into the equation of the tangent line, and plug 3.1 into the equation of the function, into y equals x squared. And I'll check work. Sketch the parabola y equals x squared. And I know you all know what that looks like. I'm sorry I'm missing the origin. I can maybe fix it. No, I can't. Whoa. Yeah, maybe I can. This gives me, yep, I can. Okay, we were asked to write the equation of the tangent line at x equals 3. When x equals 3, what is the y coordinate of that point on the parabola y equals x squared? 9, right? So we're writing the equation of the tangent line to this graph at the point 3, 9. Now, the only thing I need to write the equation of the tangent line other than a point on the tangent line, which I have, is the slope of the tangent line. What do you need to get the slope of the tangent line? The derivative. Hi. You can just grab it from a desk where... Is there a desk that has it on it? No? Yep. Sure. Okay, so what's the derivative of our function? 2x. Now, we want to know the slope of the tangent line at the point 3, 9. Which coordinate do I need to use? The 3, because the derivative is 2 times the x coordinate. So if we want to get the slope of the tangent line, we want to get f prime of 3, which equals 6. Now we know the slope of the tangent line is 6. We know it goes through the point 3, 9. We can write the equation of the tangent line. This is old. Yeah, that's why it's supposed to be very comfortable to help. All right, so to write the equation of the tangent line, it's going to be y minus, which is 9, good, equals the slope, which is 6, and then in parentheses, x minus 3. Now, let's just solve for y. Let's get y by itself. Let's just add 9 to both sides. I don't want to distribute. I have my reasons. It's not wrong to distribute. It's just going to be easier to work with. So that means that y on the tangent line is equal to 6 times x minus 3 plus 9. equation of our tangent line. Question. Now we tend to call functions f of x, we use f of x for y or g of x. For tangent lines, sometimes you're going to see L of x, like L for line. So another way I could write this, instead of just y equals, I can write L of x equals. So we have that, the equation of the tangent line. And then the other thing I wanted you to do was to plug 3.1 into the function and plug 3.1 into your tangent line equation. So let's first plug the 3.1 into our tangent line. And we'll be finding the y coordinate on the tangent line when x is 3.1. See why they want to distribute? Because it's so nice. 3.1 minus 3. 0.1 times 6. 0.6 plus 9. 9.6. So when x is 3.1, y on the tangent line equals 9.6. Let's see what y on the function is equal to when x equals 3.1. Well, I want it to be close to 3. 3 is my favorite number. So if we plug 3.1 into the function, we square it. Actually, I need your help for this because I forgot what it turned out to be. What is it? 9, can you go out a little bit more? 9.61, because I don't want people to think, oh yeah, I can always. It's 9.61? That's it? Woo! Look how close these are. Wait a minute, what is going on? Coincidence? Everyone have that, those numbers down? All right, well, if you look at the graph, all right, my graph isn't perfect. Let's go to the calculator. Let's take a look at this. I'm a little disappointed in my graphing skills. Wow, I already got a great window. If you go to y equals, and you put in the function, x squared, and put in the equation your tangent line into y2. And maybe we'll start looking at it like with the zoom 6. That takes us negative 10 to 10. Negative 10 to 10 on the y-axis. I want to zoom in on the area around where we drew the tangent line at that 0.39. It's up here. Now, if you want to just see a small part of your graph, have you ever used Zoombox? You've used Zoombox? Okay, what you do, if you just want to see a particular region, we're going to go zoom 1, and we're going to just move with the left, right, up and down arrows till we get to the upper right-hand corner of our window. It doesn't matter, one of the corners of our window. And you're going to press enter, and then you're going to move down to the opposite corner of what you'd like your window to be, and press enter. And it'll actually just focus in, it'll make that your window. So I'm going to press zoom 1. I'm going to move to one corner of my window. I want it to be way up here. Well, that's annoying. Move up to, and you can see the x and y coordinates here, so that makes it kind of nice. All right, I'll say I want it to be that to be one corner, enter. And then I move down and across, and you'll see the window growing. Yeah, that's good. I like it. And you press enter, and you'll see that little part of the graph. Oh my gosh. Wait, I think only one of my graphs graphed. Wait, where's my other graph? I only see one. Oh, wait, did I graph it? When you hit trace, it'll tell you in the upper left-hand corner what graph you're on. I'll tell you the coordinates. So I'm moving along the parabola. But if you use your up or down arrow, you can move to the other graph. Now I'm on the tangent line. What? And you can move along. How close do they look? Right? Pretty close. Why, they're so close that I feel pretty comfortable using the tangent line equation as a cheap, easy replacement for the actual function. Because if you zoom in on any graph, I don't care how crazy it is, if you zoom in close enough, it's going to look linear. It's going to look like a line. So it makes sense that we can use a tangent line to approximate a function as long as we're in an area that's close to where we drew the tangent line. Like this tangent line would not be a good approximation of y equals x squared when x is 7. It wouldn't even be close. But where we drew it, yeah, like we plugged 3.1 into the function, we plugged 3.1 into the tangent line, very close. So that's the idea today, that we can approximate a function with a tangent line. It's called linearization. And if you can write the equation of a tangent line, you got this. Okay. I would like you to, just to really solidify this in your heads, I didn't draw a graph. I'd like you to draw a graph of a function y equals f of x. And at an x value a, which I have labeled, I want you to draw a tangent line to the graph that you draw. Yeah, just make sure you can draw in the tangent line at x equals a. And I put C nearby. So C is like a nearby x value. So y equals f of x is the actual curve. Y equals L of x is our tangent line. And I wrote over there that L of C, that's y on the tangent line when x is C, is approximately equal to f of C. That's y on the actual curve when x is C. Does that make sense to you, that as long as you don't go too far away from where you drew your tangent line at A, these y coordinates on the tangent line and on the curve are going to be very close? Right? And so we're going to approximate functional values using the y coordinates on tangent line. You like it? Yeah. Now, before you panic when you see this, I have all this stuff. I want you to take a look at this line right there. What is that? That's just the equation of the tangent line where at x equals a, right? This is just the equation of the tangent line. That's how you write the equation of a tangent line at a using point slope. Okay, tell me what we do to go from this line to the line underneath it. You guys see that? You're just solving for y. So you just add f of a, the y coordinate of the point on the line, to the other side. So we just solve for y. So when you want to get the equation of a tangent line at a, and you just want y equals, the only thing that's different maybe is the plus. Instead of having a minus f of a on this side, we could just add it. And this is something that you want to know. You don't have to memorize it. I think you guys know how to write the equation of a tangent line at a. You know the slope, you plug a into the derivative. The y1, you plug a into the function. So, you know, like people will spend time memorizing L of x equals, well, L of x is just y, right? And everything else is just what you've been doing. All right. So we're going to use tangent lines to approximate functions. First one, bam. Oh, no, we're not. Not quite yet. Okay, we are going to approximate f of c by plugging c into the equation of the tangent line. Bam. All right, now we're doing the first one. Now we got to the first one. Before we start this one, did you guys know what y equals sine x looks like? When x is 0, sine of x equals, or what is sine of 0? Like, yeah, it's 0. So this is what we're talking about. Y equals sine x. And the first thing we're asked to do is to find a linearization, L of x, so write the equation of a tangent line, at x equals 0. At x equals 0. Now, you already told me what the sign of 0 is, so you know the y coordinate is 0. We just have to write the equation for the tangent line. Bless you. What's the one thing we need to write the equation on a tangent line? The slope. So to get the slope of the tangent line, what do we got to find? The derivative. So if the function is sine of x, what's the derivative? Cosine of x. Now, we don't put cosine x in for the slope, right? We always have to plug a number in. What number do we have to plug into our derivative? 0. Because so we want to get at prime of 0. That's our slope. What is the cosine of 0? 1. There's our slope. So we know the slope. We know the x and the y coordinate of the point on the tangent line. We're ready to write it. And I think we're so good that we're just going to write L of x equals. I don't know, maybe. So what's the first thing I write when I have L of x equals? What do I need to write first? Well, remember we had, first we need the slope, right? Now, we're going to have x until we plug a number in. And we'll have x minus the x coordinate of the point plus the y coordinate of the given point. All right, so what am I going to write here? The first thing is the slope, so it's 1. And then inside goes x minus the x coordinate of the point. So x minus 0. And then outside we have plus the y coordinate, so plus 0. Oh, so the equation of this tangent line is just y equals x, or L of x equals x. Oh, that's easy to work with. Isn't that easier to work with than the sine function? I think so. So we have L of x is equal to just x. And they want us to use that linearization to approximate the sine of 0.1. So the sine of 0.1 is going to approximately be equal to L of 0.1. And what's L of 0.1? What's y on the tangent line when x is 0.1? 0.1. So we plug 0.1 into the equation of the tangent line. That we can do, right? Let's see how good this is. I don't even think this is going to be good. We got to be in radian mode or it will not be good. So we said L of 0.1 is equal to 0.1. What is the actual value of the sine of 0.1? So not approximating in radian. 8 bloody blah, because it's irrational. It's on forever. Pretty good, right? Pretty good. It's approximation. So this gives us a great way to approximate values. If we can write the equation of a tangent line, those tangent lines are just fun to work with. You got this one? You ready for another? Yeah. Please, sir, can I have some more? Sure you can. All right, before we start this one, what does the graph of y equals the square root of x look like? Show me. Okay, that was good. You guys are good. Square root of x, bam. Okay? That's what y equals the square root of x. We want to find a linearization, L of x at x equals 25. Well, that's just a fancy way of asking us to write what? Because I want it to seem less scary. So what are we doing? We're writing the equation of the tangent line. When you see find a linearization, what? No, it just means write the equation of the tangent line at x equals 25. So at x equals 25, let's say that's right here. Ooh, do we know the y coordinate of that point? 25, 5, right? So we know the point. and we're writing the equation of the tangent line. Now we just got to get the slope. What do we do to get the slope? Find the derivative. What's the derivative of the square root of x? And I want it like in radical form, not with negative exponents or anything weird. 1 over 2 rad x, because it's 1/2 x to the negative 1/2. And what number do we have to plug into that derivative to get the slope of the tangent line? 25, the x coordinate of our point there, because it has an x in it. So the slope is 1 over 2 rad 25, which is equal to 1/10. Yeah, that looks like it has a slope of 1/10, right? All right, let's write the equation of that tangent line. So 1/10, the slope goes first. Then what goes in the parentheses? X minus 25, and then outside, plus the y coordinate, plus 5. Is that easy, Schneedy? No. All right, maybe it's not. But we're going to use this tangent line to approximate square roots of numbers that are near 25. Because as long as you don't go too far away from 25, the y on the tangent line is very close to the y on the actual square root of x squared. Aww, bless you. Okay, so we want to approximate the square root of 27. So so the square root of 27 is f of, if f of x equals the square root of x, then the square root of 27 is equal to f of 27, not the square root of 27. That's what the function does to it. And we're going to approximate f of 27. What are we going to approximate it with? L of 27. So we're going to plug 27 into the tangent line equation. Instead of trying to figure out the square root of it, we wrote the tangent line equation. So it's going to approximately be equal to, we had a 1/10 times 27 minus 25. You don't need calculators for this. It's so great. What's 27 minus 25? Times a 10th? 1/5 or 0.2, right? Plus 5. Don't touch that calculator. Those things are exploding like those hoverboards or whatever those things are now. They're just bursting on fire lately. 5.2. Yeah, I mean, sometimes I scare. See, it's true. And maybe your calculators will do that, kids. You don't know. Yeah, so wait a minute. This is 5.2. So we're saying the square root of 27 is approximately 5.2. Wait, I got to write that down again. Okay. So f of 27, you said 5.196? Whoa! This is pretty good, don't you think? Pretty good, right? It's nice. I mean, it's an approximation. It's not exact. Pretty good. Now, not only can I get pretty close, I also can look at the graph and tell whether or not my approximation is under or over. You see that graph of the square root of x? Is that concave up or down? It's concave down, right? I know that before I even got my approximation, if I drew a tangent line here, and I use the y on the tangent line as my approximation, is it greater than the actual or less than the actual? It's greater. It's greater. It's an over approximation. See how the y on the tangent line is over? It's above the y on the actual curve. So my approximation, I already know, is a little over the actual. So not only can you get approximation, but by looking at the concavity, you know whether it's an under or an over approximation. Oh, this is good. This is good. Can it get better? It could. No, it can. Oh, no. Knew that she was going to make it difficult and make me hate it. That's what they're thinking. The next one says, use a linearization to approximate the cube root of 9. First of all, I didn't even say what the function was. And second of all, I didn't even say where to draw the tangent line. All right, don't read it. Don't start doing things you haven't done. All right, I filled some stuff in afterwards, and I was sorry I did, because you wouldn't even have to know. I put that in because I felt sorry. But here's the thing. If you're not given a function, they say, approximate the cube root of 9, just put an x in for the 9, right? So the function itself is just f of x equals the cube root of x, which looks like that. Oh, I missed it. What? I can fix it. No, I can't. So forget that. Now, we're asked to approximate the cube root of 9, which is the y coordinate on the graph when x is 9. I don't know what that is. So I'm not going to write the equation of a tangent line there because I don't know the y coordinate of that point, and I wouldn't need to approximate it if I knew it. But is there a value near 9 whose y coordinate on this graph I know? 8. So doesn't it make sense that I would want to draw the tangent line when x is 8? Because at 8 we know the y coordinate. What is the cube root of 8? 2. So we're going to write the equation of the tangent line at the nearby point 8,2, and then we can plug the 9 into that. We'll find. So, oh boy, what do we need to do? Well, we got to get the derivative. So the function is the cube root of x. You ready to give me that derivative? Yeah? All right, let me hear it. What? All right, that's right. Okay. Nice. Now, what number are we going to plug in? Where are we drawing the tangent line? At 8. Right? This way everything's going to work out nicely. So you plug in the x value at the point we're drawing the tangent line. So we want f prime of 8. 1 over 3 times the cube root of 8 squared. What's the cube root of 8? Square it. Times 3. So we have 1 over 12. That is the slope of our tangent line. Let's write the equation of our tangent line. But instead of y, we're going to use L of x. All right. L of x, y on the tangent line. What's the first thing I got to write? The derivative, the slope, which was 1 over 12. What goes in the parentheses? X minus 8, and then plus the y coordinate of the point. Nice. Now we want to approximate f of 9. The cube root of 9 is just f of 9, right? We want to approximate that with what? L of 9. We're going to plug 9 into the equation of our tangent line. This way we won't be taking any cube roots of things we can't do. We'll only be adding and multiplying. All right, so we plug 9 into the x of our tangent line. We have 1/12, 9 minus 8 plus 2. 9 minus 8 times 1/12 is 1/12 plus 2. 2 and 1/12. 2 and 1/12 is approximately equal to 2.083 repeating. Okay. Let's see how close this is. So for L of 9, so the y coordinate on our tangent line when x is 9, we got 2 and 1/12, which was equal to 2.083 repeating. The actual value of f of 9, or the cube root of 9, is equal to 2.08. What? And it comes next? Okay. Pretty good, right? Now, are you going to be intimidated when someone says to you, use a linearization? No. No, you're not going to be intimidated because what does that mean you have to do? just write the equation of a tangent line and use that, which is a nice thing because they're very easy to plug numbers into. So to find a linearization of a function, that just means write the equation of the tangent line, right? The equation of, oh shoot, I didn't realize this late. A tangent line to y equals f of x. To approximate f of x. To approximate. If a function is concave down, and I use a linear approximation to approximate my function, is my approximation going to be over or under? Over. And if it was concave up, it would be an under approximation. Now, one thing I feel a little bad about, I didn't go to this. I wanted to show you. So in the homework problem, yep, the volume of a right circular cylinder is pi r squared h. That was 1,000. So that gave us h is 1,000 over pi r squared. You had to plug that into the area formula, surface area formula we're trying to minimize. The pi and the r should have canceled. So you should have been left with one variable. The area would have been 8r squared plus 2,000 over r. Then you had to take the derivative. Oh, I should have written the derivative. Equals 16r, and it would be minus 2,000 over r squared. We set that equal to 0. We move the negative term to the other side. Cross multiply. And when you do that, you get r cubed equals 125, which makes r equal to 5. When you want to make sure it's a minimum area. So the radius had to be greater than 0. So I could start my sign chart for a prime at 0. You mark it off at 5. You take a prime of 1. A prime of 1 would be 16 times 1 minus 2,000 over 1 squared, negative, then positive. So the area is definitely a min. Oops. And then you had to go back and get the height, which you got by plugging in for h. 40 over pi, so the ratio 40 over pi over 5 is 8 over pi. Oh, and your handout, have fun with that. Number 3, you're trying to approximate the 0 of the function, so plug 0 into y of your tangent line and solve for x.